Dear students, in this video I will explain chemical kinetics. We know that chemical kinetics explains about the speed of reaction. In thermodynamics in class 11 we have studied the whether a reaction is possible or not. Means from the Gibbs free energy we know that if the Gibbs free energy change becomes negative, then we predict that a chemical reaction is feasible, possible. But thermodynamics do not explain about the speed of a reaction, means how quickly a reaction can be possible. For that we need to study chemical kinetics. So kinetic studies helps us to determine the speed or rate of a chemical reaction as well as conditions by which the reaction rate can be controlled, such as concentration, temperature, pressure and catalyst. Now, rate of a chemical reaction can be expressed as the rate of decrease in concentration of any one of the reactants or the rate of increase in concentration of any of the products. That means during a reaction, concentration of reactant decreases, and rate means with time how its concentration decreases, and also it can be explained with time how the amount of product increases. So for a hypothetical equation, hypothetical chemical reaction from reactant to product, assuming that the volume of the system remains constant, then if at time t1, initial time, the concentration of reactant and products are R1 and P1 respectively, and at time 2, means at a final time, the concentration of reactant and product are R2 and P2 respectively, then the change in time is the final time minus the initial time. Then change in concentration of reactant is equals to the final concentration of the reactant minus the initial concentration of the reactant. We can follow that the concentration of reactant decreases, that is the final value is less than the initial value, therefore this value will be negative. Now the change in concentration of product is also the concentration of product final concentration minus its initial concentration, and since in a chemical reaction product's concentration increases, therefore the final concentration will be more than that of the initial concentration of the product, hence delta P will be positive. Here the parentheses that are used, square bracket, expresses, it is used to express the concentration of reactant and product. Now the rate of disappearance of R, that means the rate of reaction can be explained as the rate of disappearance of R, which is equals to decrease in concentration of R with time. So it is minus dr by dt. Now this actually delta R by delta T, this delta R by delta T, it explains large difference in concentration with larger time interval. So this ratio can be expressed as the explained as the average rate of decrease in concentration of reactant. Similarly, the average rate of appearance of product will be the increase in concentration of product with time. That means delta P by delta T, delta concentration of P by delta T. Now then what should be the unit of rate of reaction? Since on the numerator it is the concentration, which can be explained as moles per liter, and the time, if it is taken in second or if it is taken in minute or hour, accordingly it will be moles per liter per second or moles per liter per minute, like that. So Here it is written as the unit moles per liter per second if the time is taken in second. Then the average rate, which is this larger change in concentration of reactant or product with a larger time interval, this average rate cannot be used to predict the rate of reaction at a particular instant, as it would be constant for the time interval for which it is calculated. So, to express the rate of a particular moment at a particular moment of time, we determine the instantaneous rate. It is obtained when we consider the average rate of rate at the smallest time interval, say dt. That means when this delta t approaches 0, means in a very small time interval, the change in concentration of reactant and product, which is denoted by this d, small d, dr by dt, this is the ratio minus dr by dt. This explains the instantaneous rate of decrease in concentration of reactant, and it is the instantaneous rate of formation of product. So graphically we can explain that if concentration of reactant is plotted with time, then here we can follow that at time t1 the concentration of reactant was R1, which is larger value, and at time t2 the concentration of reactant is having lower value. Since the concentration of reactant decreases, we can follow in the graph that initially at time 0 the concentration of reactant is maximum, and with time it decreases gradually, and it will this line will never touch the time line. That means it will not cut the x-axis, because at equilibrium the forward and backward reaction becomes same. Rate of the forward and backward reaction becomes same, means the concentration of reactant can never be totally 0, means at equilibrium again from the product the reactant is also returned back, so there will be some concentration left over for the reactant. Now you follow that in this time interval T2 minus T1, this T2 minus T1, the concentration change is R2 minus R1. Since R1 is greater than R2, the value will come the negative value. Now for a very small time interval, if we say calculate at this time t, which is denoted as the instantaneous rate, means for a very small time interval, which will be dt here, which is almost constant, and that means in that small time interval the concentration change here is also very small. So this ratio can be treated as the instantaneous rate of formation, decrease in concentration of reactant. And here in this graph we can say that concentration of product when plotted with time, then in that time interval T2 minus T1, this is the change in concentration of the product, that is del P2 minus P1 divided by delta T, that is T2 minus T1, and at a very small time gap delta T the concentration of product changes as dP. So this must be the rate of change of formation of product, that means rate of formation of product instantaneous rate. So in this way graphically we can explain the rate of formation of product and rate of decrease in concentration of reactant. Now for example, for the reaction decomposition of HI to form hydrogen and iodine, following this chemical reaction, the rate can be written as minus the concentration change of the reactant. Now here 2 moles in the reaction, hydrogen iodide is having 2 moles participating in the reaction. So per mole change of concentration of the reactant HI to calculate that, we have to divide this value with 2, this mole number. So the per mole formation of the product hydrogen is written as delta concentration of H2 by delta T, and similarly for the formation of I2 it can be calculated. Now from these relations, on the basis of this kind of relations, we can solve if we have given the rate of decrease in concentration of reactant, then we can calculate the rate of formation of any one of the product. I mean, among the products, any one it can be calculated. That means for each product it can be calculated, and the vice versa. If products are given, then rate of decrease in concentration of reactant can be calculated. Let us see this numerical. The decomposition of N2O5 in CCl4 at around 318 Kelvin has been studied by monitoring the concentration of N2O5 in the solution. Initially, the concentration of N2O5 is 2.33 moles per liter, and after 184 minutes, it is reduced to 2.08 moles per liter. The reaction takes place according to the equation, this one. So 2 moles N2O5 decomposes to 4 mole NO2 and forming 1 mole O2. Now it is asked to calculate the average rate of this reaction, and also what is the rate of production of NO2 during this time period, means during 184 minutes. So we can write average rate of the reaction, that means minus half delta concentration of N2O5 by delta T. So you follow that this was the final value, concentration it was given, and minus the initial value divided by the time interval 184 minutes. So the value came here 6.79 into 10 to the power minus 4 moles per liter per minute. Now here we need to calculate, this is the rate of the reaction, rate of the decrease in concentration of the reactant, and here we have also asked to calculate the rate of production of NO2. For that, the rate of the reaction can be stated as, it is 1/4 the rate of formation of NO2, I mean change in concentration of NO2 with time interval. So it can be related to the reactant concentration, rate of decrease in concentration of reactant by this equation. So here from we can calculate this delta NO2 by delta T as, it is, if we use this value, it is given here, you can follow that this value was there, 6.79 into 10 to the power minus 4. So we can put this value here and it will be multiplied with 4 to get the change in concentration of NO2 with time. So the value is coming as 2.72 into 10 to the power minus 3 moles per liter per minute. So this was about the introduction of this chapter. In the next videos we will find the next parts. So up to this we can learn how the rate of formation of product and can be calculated, and also the rate of decrease in concentration of reactant can be calculated. Thank you.